Okay, we are on to the very last chapter summary for further maths for Core Pure Year 2, which is chapter 8, Modelling with Differential Equations. And this is one that feels a lot more similar to what you might expect to see in an exam question. However, like I always say, it is not possible for these chapter summaries to cover all of the possible ways that examiners can assess the topic. This is here to just kind of like brush up on what was in the full playlist, but do make sure you're going and doing a lot of preparation if you are taking exams in this topic. So we're going to look at 3 questions in this one. We're going to begin by looking at a first order, and there are plenty of equations that are first order that are in context for modelling, but I think the one that I wanted to look at in more detail was for stuff to do with liquids in a container where things are kind of mixing together. So we're going to read through this question and then we're going to kind of jump back over to this description that we have over here. It says that a large glass container initially holds 20 litres of pure water. A red dye solution is added to the container at a rate of 4 litres per minute, immediately mixing on entry, and liquid is removed from the container at a constant rate of 2 litres per minute. So we've got red dye solution being added in and immediately mixing with the water, and then that mixed liquid is being removed at a constant rate of 2 litres per minute. The first thing we're going to do, it says, given that there is X litres of red dye solution in the container after T minutes, show that the situation can be modelled by this differential equation that we've got here. Okay, we'll come back to this box with the extra writing in just a second. This is talking about how the red dye is changing dx dt. This is the red dye and this is per time. So I think the 4 is the one that's really obvious because it is just being added at 4 litres per minute. So the amount of red dye will be increasing by a 4 for this rate that we've got here. And then I want to work on this part, which has got a minus with it, meaning it's to do with the amount that is leaking. And it's definitely to do with this liquid that is being removed here. So before we actually answer this question, let's try and look at some of the theory about liquids in tanks and how we can try and get the rationale behind what this happens. So it says, for example, if a tank had a constant volume of 30 litres and 3 litres of the mixed liquid is being removed every minute, then 3 out of 30, 3 litres out of the constant volume of 30 of whatever in the tank, the water, the contaminant, the dye, whatever it might be, is being removed. In other words, 3 out of 30 as a proportion is a tenth. So we're saying that whatever is in the tank, a tenth of the water is being removed, a tenth of the contaminant is being removed, a tenth of the dye is being removed, because it's all being mixed together. So if X is the amount of, in this case, dye that we have, we would say that 3 out of 30, that proportion of the dye, of being a multiplication, is being removed, and 3 out of 30 is the same as a tenth or 0.1. So this is the amount that is being removed. We're trying to think of it as the proportion of whatever is in there. So if we extend this idea to a tank that maybe doesn't have a constant volume, but just has a volume of V litres, and L litres are being removed every minute, it should say, not every minute, but I will change that in the PDF, then the proportion that is being removed is L out of V, 3 out of 30, the amount being removed out of the total volume, the amount being removed out of the total volume. So this proportion of whatever is in the tank is being removed. So if we're interested of how much of, I don't know, X might be the amount of red dye, it might be the amount of pollutant in there, that fraction of that thing is being removed. So that's the way I like to think about this. There are other ways of thinking about it because it is proportion, and there are plenty of ways of reasoning through proportion. But I like to think, what is the proportion of materials inside that tank that is being removed every unit of time? And we just multiply that proportion by the thing that we're actually examining. So having a look at this question again, I'm going to begin by just explaining the first part that we have here. So I can say that dx by dt equals 4, and this is just going to be because 4 litres of red dye X is added every minute. Easy. That's the easy part. Is added every minute. However, we now want to figure out this part where we have the volume and the litres. Now for this question, the volume is actually not going to be a constant volume because there are 20 litres to begin with, 4 litres are being added, 4 litres of liquid are being added every minute, and 2 litres are being removed every minute. So the volume at time t, it starts with 20. Every minute, 4 litres are being added, so that's 4 times by the number of minutes, and 2 litres are being removed every minute. So this T part is because, depending on the number of minutes, there'll be a different volume that we have there. So the volume of this tank at time t is 20 plus 2t. If there's an extra 4 and 2 are being removed, every minute there are 2 extra litres that we have here. And we know in this question that the amount of liquid that is being removed is 2 litres. So we can say the proportion of liquid, dye, water leaving is 2 litres out of 20 plus 2t. So this now means that the amount of dye, which is x, leaving, well, if there's x in there, it would be, imagining this is like a percentage or a fraction, it would be this amount of x that is going to be leaving. In other words, 2x over 20 plus 2t. Hence, we can now say that dx dt is equal to 4 that is arriving, and it's leaving, so it's going to be a negative, which is 2x over 20 plus 2t. So when I simplify this, I can divide the top and bottom of the fraction by 2, so that I get 4 minus x over 10 plus t that we've got here. And this is definitely enough explanation to give us all those marks that we've got there. And then part B of the question says, find the amount of red dye solution in the container after 5 minutes, and hence the concentration of the red dye solution as a percentage. Well, let's just deal with this first part. We're going to find the amount of red dye solution in the container after 5 minutes. In other words, we are going to solve this differential equation that we've got here. I haven't put a reminder of how to do this. You should have had a look at that in the previous chapter summary. But this is a first order differential equation. So even if you couldn't do part A of the question, we can definitely solve this by doing our integrating factor. Now we do need to have it written in that standard form. You know, the standard form is our dy by dx plus p of x y equals q of x. So I'm going to rewrite this equation that's up here in a slightly different form so that we have a dx dt plus, I'm going to have, instead of the y, it's going to be the x, and I'm going to write it as the 1 over 10 plus t. I've just taken this and I've added it to the left-hand side, and I've also split it so that I've got my function of t and my x. So it would be the function of t instead of x, and instead of y, it is the x here. Different letters can make these questions really confusing. And on the right-hand side, there is the 4. So my p in this case, my p of t is my 1 over 10 plus t. So my integrating factor is going to be e to the integral of p of t dt, which is e to the integral of 1 over 10 plus t dt, which is e to the ln of 10 plus t, because obviously that's what 1 over 10 plus t integrates to, and that e and the ln cancels, so we just get 10 plus t is the integrating factor. So this means we now take this equation and we multiply it by 10 plus t. So we have a 10 plus t multiplied by dx dt. That bit just disappears, so we just get x, and then we have 4 multiplied by 10 plus t. So on the left-hand side, this is going to be the form of the reverse product rule that we were expecting. It is something has been differentiated by t to give us this, and it is 10 plus t x. It's usually easiest to look at this. You have the 10 plus t and the x part there. And if you check the product rule when you differentiate this, you do actually end up with this thing over here. And this is equal to, I'm going to expand the brackets because I then get 40 plus 40, because in a moment I'm going to be doing some expanding. So my 10 plus t x is going to be equal to the integral of 40 plus 40 dt. It's like this dt here has come up here and been multiplied by it, and then we do an integration. So my 10 plus t x is equal to 40t plus 2t squared plus c. And we know something. When the time is equal to 0, how much red dye was in the tank? How much red dye was in the tank when it started? Oh, it was just pure water. There was no red dye solution at all. So we can say that x is going to be equal to 0. So what we end up with to find out what c is, on the left it's just a 0. We then get a 0 plus c. So c is equal to 0. So now I'm going to go right back up here so that I have a bit more space for this. Now c is equal to 0. This tells me that my equation is 10 plus t x equals 40t plus 2t squared, meaning that x is 40t plus 2t squared over 10 plus t. So we've solved the differential equation, we found the general solution, we found the particular solution, and now we're actually going to go and see what the question wanted for us to do. What the question wanted us to do. So it says find the amount of red dye in the solution in the container after 5 minutes. Fine. So we're now going to say when t equals 5, let's find out how much red dye there is in the container. So I'm going to just substitute 5 into this. So it's 40 times by 5 plus 2 times by 5 squared divided by 10 plus 5, and we get the amount is 50 over 3, which is 16.7 litres to 3 significant figures. If they don't ask, 3 significant figures is what they're expecting. And then it says, hence find the concentration of the red dye solution as a percentage. In other words, what of the tank is red dye solution? So we just need to now find out what is the volume when the time is 5 minutes. So when t is equal to 5, the volume of the tank is 20 plus 2 times 5. Now, where am I getting that from? Do you remember we talked about this earlier on? We said that the volume of the tank is this. So if I now know that there is this 16.7 litres that are red, I want to find out how much there is in the tank in total to know what the concentration is in the tank in total. So I will do the 20 plus 2 times 5, which is just 30. Hence, the concentration is... I'm going to do not the 16.7, I'll do the accurate. So I'll do the 50 over 3 over the 30. So it's 50 over 3 divided by 30. It is 5/9. And if I change that to a percentage, if I do 5/9 times by 100, because it wanted it as a percentage, we get that the concentration is 55.6% to 3 significant figures. Okay? So... that was a pretty tricky question, I think, especially with this idea of the concentration. You have to say how much of the total liquid is the red dye solution. For part C, it says when the amount of red dye solution makes up at least 45% of the liquid appears opaque. Find according to the model when the liquid first appears opaque to the nearest second. Well, it's 55.6%, so it's already appearing opaque at 5 minutes. So I'm expecting it to be somewhere before 5 minutes that it will have got to this 45% where it begins to appear as something that is opaque. I wonder if I'll be able to fit it in here. I'm probably going to need to have a second page. So I'm just going to add one in right now so that I don't make it too messy. So for part C, we are going to be saying that the amount of contaminant out of the total volume is going to be 45%. Not the contaminant, excuse me. The amount of red dye out of the total volume is 45%. Now, I know that the volume is 20 plus 2t. And I know that the x expression is this thing up here. So although this is going to look kind of messy, I can actually have like a fraction within a fraction where I have my 40t plus 2t squared, go away calculator, plus 2t squared over 10 plus t. So that is the x part. Whoops, that is the x part, and then this is the volume. It should make sense. The amount of red dye out of the total volume when it gets to 45%. That's the thing I'm trying to solve. And so this is going to be equal to 45%, which I can just write as 0.45. So we just need to solve this equation. I'm going to multiply up by the 20 plus 2t. So 40t plus 2t squared over 10 plus t is equal to 0.45 times by 20 plus 2t. Well, I'm also going to have to multiply it up by this 10 plus t. So let's leave the 0.45. I have a 20 plus 2t, a 10 plus t. However you want to do this, this is just the way I'm going to go about solving this. I'll leave the 0.45. When I expand these two brackets, 20 times 10 is 200. I then have a 20t and a 20t, so that's a 40t, and a 2t squared. Looks like we've got a quadratic going on here, okay? So I have a 40t, a 2t squared, 0.45 times 200, is that 90? Yeah, that's 90. Can't be too sure with these things though. So we have a 90, 0.45 times 40, that is 18t, and 0.45 times by 2t squared is 0.9t squared. So if we just solve this, we should find the time when the amount of red dye out of the total volume is 45%. In other words, when it becomes opaque. So I'm going to put the quadratic onto the left-hand side. I'll do the 2 minus the 0.9 for the t squared. That's 1.1t squared. I have the 40t minus the 18t, which is 22t. And then I have the minus 90 is equal to 0. So going to my equation solver on my calculator, this is going to be for my polynomial degree order 2. 1.1, 22, and minus 90. It gives me two different solutions. It gives me a t equals minus 23.48. Obviously, we're going to reject that because we can't have a negative time. Or 3.4839, and this is in minutes. But I don't know if you remember this. The question actually asked for it to be written to the nearest second. So I am going to say, I'll give it in minutes and seconds. If you wanted to, you could give it all in just in seconds. I'll show you both of them. So I just need to do a conversion of the 0.4839 part into seconds. I'll multiply that by 60. So 0.4839 times by 60, that is 29.03, in other words, 29 seconds. So it first becomes, or appears opaque, at 3 minutes and 29 seconds. Alternatively, 3 minutes and 29 seconds, I can do 29 plus 3 lots of 60. This is 209 seconds. Obviously, that would also have been accepted as an answer for this. And then we have part D and part E. It is observed that the liquid becomes opaque after 3 minutes and 40 seconds. Evaluate the model. So we said it was 3 minutes and 29. In reality, it is saying that it's after 3 minutes and 40 seconds. So 3 minutes and 40 seconds, we're going to compare this to 3 minutes and 29. We just said that 3 minutes 29 seconds was 209 seconds. So 3 times 60 plus 40 is 220 seconds. They're pretty close, right? Now, the way I like to decide if they are kind of close enough to each other is I will do the comparison between them. I'll do what our estimate was divided by the true amount, and I will multiply it by 100 to get it as a percentage. So if I do 209 divided by 220 times by 100, I get that it's 95%. So our model underestimated by 5%. Now, if you've seen any of my videos on stuff like this before, I generally say if it's within a 10% range, if it's 10% below or 10% above, then it's a pretty good model. Anything more than 10%, it's probably a bit too far away. So our model underestimated by 5%. This means it is fairly accurate, so it's a good model. This means it is fairly accurate, so is a good model. When they say evaluate the model, they're really saying, is it good? Is it bad? Something like that. And then for part E of the question, it just says criticize the model. There are plenty of things we could be saying. We could criticize that the rate of liquid being removed is unlikely to be constant. It's unlikely to be added at a constant rate. But I think the most unrealistic thing in these liquid kind of questions is that it immediately mixes on entry. So I'm just going to do a bit of a criticism of that and say it is very unlikely, or it is unlikely, it immediately mixes on entry. There's other things that might be accepted for these kinds of things as well. Wow, what a question. So, modelling with first order, plenty of things to think about here, especially this stuff to do with liquids in a tank. The more you practice them, the more you'll just get used to that kind of style of questions. So I'm going to do a second order one, and then I'm going to be doing the kind of new skill in this one, which is coupled differential equations. So, quick reminder about how you do solve these. You form the auxiliary equation and you solve that. It tells you what the complementary function is. Find the particular integral if necessary. In our question here, it is necessary because we have something on the right-hand side. And you do that through differentiation, substitution, and solving. Your general solution is then the complementary function plus the particular integral. And because it's a modelling question, you're pretty much always going to need to find a particular solution by substituting in the given conditions in the question. So, like I said, the theory of all of this stuff was covered in the previous chapter summary. This is really looking at it in a modelling context. It's unusual for us to need to set this up, by the way, for a second order. They often like you to do the setup for a first order differential equation. I haven't really seen many questions where they need it to be done like this. Most of them in the textbook are to do with damping. I will discuss that later on as well. So it was kind of hard coming up with these questions myself. I do write these questions myself. This one says, a scientist is observing the effect that an external stimulus has on the concentration of a particular chemical inside a bacterium, the singular of bacteria. The concentration of the chemical, X micromoles per litre, that's just the way that you write micromoles per litre, is modelled by the following differential equation. So we have this whole thing here. I'm not even going to read it out. You can see what it looks like. It's just worth noting that we do have something on the right-hand side, so we will need to do a particular integral. You may not always have them like that. You might have it being equal to 0, in which case you can skip all of the particular integral stuff. So the first part is literally just find a general solution of this differential equation. Nothing to do with the model at all. So I will begin by doing the auxiliary equation, looking at this left-hand side that we've got here. And this is going to be m squared plus 0.4m plus 1.04 is equal to 0. So on my equation solver, I'll put in the coefficients of 1, 0.4 and 1.04. And this gives me that m is equal to minus 0.2 plus or minus I. Meaning the complementary function is, it's going to be an x equals, well, the minus 0.2 is going to be the e to the minus 0.2t. The imaginary part of this I is the thing that gives us the sine and cosine. So we're going to have a cosine of just t. If it had a 3i, it would be a 3t, but it's just an I, so it's by itself. And then we get a sine part like this. You could do sine then cos, but I've just chosen to do cos then sine for this. So there's our complementary function. I'm now going to do the particular integral, and compared to the previous video on the methods for differential equation, this one's a pretty simple one because I just have a constant on the right hand side. So I'm just going to try that x is equal to a constant. I'm going to pick the letter lambda. When I differentiate lambda, I get 0. And of course, when I differentiate that again, I still get 0. So this is now the part where I'm finding the particular integral through differentiation. And now I'm going to do substitution into this original equation. So when I sub it in, I get a 0. And then I get a 0.4 times by a 0. And then a 1.04 times by lambda. And that is equal to 5.2. Last step is to do the solving. So I'll just do my lambda is 5.2 divided by 1.04, which is 5. Hence we now have our general solution that x is equal to e to the minus 0.2t, a cos t plus b sine t, that's the complementary function, plus the particular integral. Okay. Now we're going to go to the start that kind of brings in a bit more of the model. So remember we were talking about an external stimulus being put onto some kind of bacterium and it's changing the concentration of the chemical inside it. Before the external stimulus is applied, the concentration of the chemical was stable at 7 micromoles per litre. At time t equals 0, the stimulus is applied. So we're now going to say this is talking about when the stimulus is being applied. And the rate of change of the concentration of the chemical is minus 6.4 micrometers per litre per second. So at the very beginning, when t is equal to 0, this is something to do with the rate of change. And when t is equal to 0, this was also what the stability state was. So to kind of like extract some of that information for part B, I can say that when t was equal to 0, basically as the stimulus was being applied, the amount of concentration was 7. And we also said that the rate of change of the concentration is this minus 6.4, okay? Now, sometimes people get a bit confused by this wording because we're saying it was this and then it was being applied at t equals 0. Well, when t equals 0, at the very, very start, the x value is 7. It's only going to change as soon as that stimulus has actually been applied there. So it's pretty obvious what we need to do, right? Even though it says find, according to the model, the concentration of the chemical after 3 seconds, in other words, find x when t equals 3, it kind of feels like we haven't finished this, right? We still haven't found a particular solution. So I'm going to use this information with my general solution to find the particular solution, and then I will find x when t is equal to 3. So I'm going to start off just using this one and this one, okay? So this means that 7, when x is 7, e to the 0 is just a 1, And then A cos 0 is just A. B sine 0 is just 0, because sine 0 is 0. And then you get a plus 5. So in other words, 7 is equal to A plus 5. And so 7 minus 5, which is 2, A is equal to 2. So to use this fact, I'm going to have to take the equation and I'm going to have to differentiate it, okay? So dx by dt. I will start off by differentiating this and keep this. Then I will keep this and differentiate this. This is going to differentiate to just nothing. It's going to go to a 0. So I think I said I was going to start off by differentiating the e to the minus 0.2t. That'll be minus 0.2 e to the minus 0.2t, a cos t plus b sine t. And then I'll keep the first part and I'll differentiate the second part. Cos goes to minus sine, sine goes to cos. Pretty straightforward here because I didn't have, I just had a t. Obviously if I had a 2t or a 3t or a half t, I'd be a bit more careful about how I differentiate it. So the dx dt is minus 6.4. I know that this part is going to be when t is equal to 0. This is a 1. So I have a minus 0.2. And then the sine parts disappear because sine 0 is 0. So I will just have the cos parts because cos 0 is 1. So that's 0.2 multiplied by a, plus for the second part, I just have b. And I worked out what a was. A was 2. So this is minus 0.2 times 2 plus b. So this is going to be minus 6.4 plus 0.2 times 2. This means that b is equal to minus 6. So we now actually have our particular solution. X is equal to e to the minus 0.2t, a cos t, minus b sine t, plus 5. And remember what the question actually wanted for us to do. It wants us to find x when t is equal to 3. So when t equals 3, I don't need to show the substitution. I can just do this on my calculator. I'm not going to get any marks for this. So I will store in my calculator that t is 3, and I'll be doing e to the minus 0.2 answer multiplied by 2 cos answer. You've got to be in radians because we're doing calculus here. Minus 6 sine answer. Close the brackets, plus 5, and we get 3.4486. I'm going to do it to 3 significant figures if it doesn't say. That's what they're expecting. That is 3.45 micromoles per litre. So I will write that this is 3 significant figures afterwards. 3.45 micromoles per litre. It then says for part C, the scientist believes that the external stimulus permanently changes the concentration of the chemical inside the bacterium. Does the model support the scientist's belief? So, for part C of this question, we will say before the concentration was 7 micromoles per litre. Let's have a look. We have this equation, x equals e to the minus 0.2t, 2 cos t minus 6 sine t plus 5. Let's think what happens as t goes to a big value. What happens as it kind of settles in the future? Now, this is going to be a trig function, right? If you combine these using the harmonic identity, as t goes to infinity, it's constantly varying up and down. However, there is this thing outside the front of it. What happens to e to the minus 0.2t as t goes towards infinity? Well, if you do e to the power of a very large negative number, it goes towards 0. Hence, this means that x is going to go towards, this whole part here is 0, and there is a 5. So we can now answer and say, as over time, the concentration settles at 5 micromoles per litre, meaning that it has changed permanently. Let's see what they've said as the wording in the question. Does the model support the scientist's belief? Well, it was 7 micromoles before. Something has happened through this process. The model does support it. They said it permanently changes the concentration. Yes, it's actually decreased it. The concentration settles at 5 micromoles per litre, meaning the scientists belief is supported, it has permanently decreased from 7 to 5. So they actually said there was a permanent change. We can go even a step further than that and say that it is a permanent decrease. Now, if you do have a graphics calculator, or even if you're doing this just as part of your revision, I would recommend putting this on Desmos or on your graphics calculator, because it shows you what's actually happening here, okay? You can see that there is this kind of sine, like sort of sinusoidal, like sine cos, like wavy motion, and that's because of this part of the graph here. We know from the harmonic identity, the r cos theta plus alpha kind of stuff, or the r sine theta plus alpha stuff. This is just one single trig function, but there is this thing here which is doing a damped motion, okay? So we have this harmonic motion, but it has a damping that is happening here. So in the textbook we talk a lot about damped harmonic motion. This is an example of it. And the reason it's settling at that 5 as time increases here is because of this extra plus 5 that we've got. So with time, this part goes to 0, and we just end up that x goes towards 5. So you can see, again, it started at 7, it immediately decreased, it actually increased up here, but then eventually it settles at 5. Okay, the next one that we're going to have a look at is a very big one, coupled differential equations. Now, these are actually one of my favourite kind of questions. There's an awful lot of stuff that goes on in one of these questions, and we can tell they're coupled because you have these two different first-order differential equations, where each of them is in terms of x and y. We have a mixture of different variables in them, and I'm actually going to come back to this context of the question after we read through this, okay? And I'm going to try and not zoom in too much because I might want to refer to these equations. So if you want a second-order differential equation later on in the question in terms of x, in other words, like this thing that we've got here, you need to make y the subject of an appropriate equation to have y in terms of x dash and x, in other words, dx dt and x are. That's going to be this one here, because I'll get y purely in terms of x. You then differentiate that thing that you've just got in terms of x dash and x, dx dt and x, so that you have it in terms of the second derivative of x and the first derivative of x. And then you substitute it into this other equation here. You put the y part in here and the y derivative part in here. And that will eliminate y, and this will give you this second order differential equation in terms of x. All you then need to do is find the general solution for this. And then I'm going to come back to point 5 when we've actually done this part that we've got here. So I'm just going to kind of pause at this point and stop. However, what I'm going to do is just quickly zoom in on this part. This should feel like the very advanced version of solving simultaneous equations. In other words, eliminating a variable through some kind of substitution. It kind of has flavours of when you probably first learnt about simultaneous equations in GCSE, apart from, my goodness, they are so much harder. So let's read what's going on in this coupled differential equation. A survey is conducted on the number of ladybirds and the number of beetles in a closed ecosystem. At time t, where t is measured in months since the start of the survey, the number of ladybirds, x hundreds, and the number of beetles, y hundreds, in the ecosystem is modelled by the differential equations. So I'm just going to quickly highlight something so that I won't forget this. X is in hundreds, y is also in hundreds, and t is in the number of months that we've got here. And so the whole point of these things is we're saying the rate of change of the ladybirds is related to the number of ladybirds that there are, but also it's related to the number of beetles that there are. So maybe if there's a lot of beetles, it's actually going to be competitive for the ladybirds. That's why there's a negative with it, and it's meaning that their population is going to actually start decreasing. Maybe for the beetles, the more ladybirds there are actually helps them because maybe they eat them. I don't know about the biology of this situation. It can be used to model predators and preys. It can be used to model two like competing species, all sorts of things. And the deeper you go with this, if you do it at university, it's a very, very fascinating area that we've got here. So we're going to take these two coupled differential equations, and we're basically going to try and eliminate y. You should notice here for this thing we're going to try and show is true, that it's only in terms of x. I should also add, this is going to be a homogeneous one where it's equal to 0. You should expect to potentially see a question where there might be some other kind of function with this as well. But for now, this one is just with 0, and you can come across those other kind in the textbook and in exam questions. So because I want it in terms of x, I will make y the subject of the appropriate equation, which is this top one, because I want it just in terms of x. I can't do it here because I have y and y in two different places. I need to make y the subject so that I can change it into everything in terms of x. So from this first one, I'm actually going to rewrite this first one, by the way. I'm going to write it as x dash, meaning it's been differentiated, equals 6x minus 4y. And this one is y dash equals 2x plus 2y. So from this first equation, I am going to rearrange 1 to make y the subject. So to make y the subject, I will put the 4y onto the left. I will get 6x minus the derivative of x, and then I'm going to divide by 4. 6 divided by 4 is 3 over 2, and then I get a quarter x dash like this. So this is the first point here. We have found y in terms of x dash and x. I'm now going to do the second point, which is to differentiate it to find y dash in terms of x double dash and x dash. So when I differentiate this, it's really simple. I'm just going to differentiate y. I will differentiate the x, and I will differentiate the x dash to get x double dash. So now that I have what y and y dash are, I can put them into the second equation. This is this part. Substitute into the other equation, eliminating y. We're not going to be left with anything to do with y. So I'm going to sub into equation number 2. Now, equation number 2 is y dash equals 2x plus 2y. Y dash equals 2x plus 2y. In other words, this y part that we've got is going to go in here, and this y dash part that we've got is going to go in there, okay? So left-hand side, 3 over 2x dash minus a quarter x double dash equals 2x plus 2 lots of 3 over 2x minus a quarter x dash. If you want to, you could... Did I even put the 2 in front of it? I didn't. There should be a 2 in front of there, shouldn't there? So this is 3 over 2x dash minus a quarter x double dash equals 2x plus 3x. 2 times a quarter is a half, so we get a half x dash like this. Now I'm going to put it all so that the main thing that's going to be positive is the second derivative, because clearly here the second derivative is positive and has just a coefficient of 1. So I will put the quarter x double dash over here. I have a minus a half x dash, and I'm going to minus 3 over 2. You know, sometimes you do the most basic things on the calculator. I'm going to do minus a half minus 3 over 2. It is minus 2 x dash. And then I have plus 5x, and that's the 2x and the 3x giving me this. So timesing it all by 4, that's x double dash minus 8x dash plus 20x. And to get it back into the form that they wanted, the second derivative will be written like this. The first derivative like this, and then we have it as this point. They had it with it equal to 0. I don't think they'd be too fussy with this. I think it's perfectly fine in the way that we've got it written. Just show that it's like this, okay? So, pretty involved part of this. Now we're going to get on with the rest of it. We've now come up with this and eliminated y. We're going to basically find the general solution for x, and then we're going to have to continue this process, and I'll talk to you about that when we get to this. So it says at the start of the study, there are 6 times as many ladybirds as there are beetles. Interesting. So when t is equal to 0, the number of ladybirds, which is x, are 6 times the number of beetles. X is the number of ladybirds. Yeah, it says the number of ladybirds is 6 times the number of beetles. And it also tells us that dx dt is 8. It's worth thinking, though, dx dt being equal to 8. Let's just think about what this is saying. Remember that x isn't measured in hundreds, and t is in months, so it's saying that 800 per month are increasing to the number of ladybirds at the start of the study. We're going to find the particular solutions for x and y. Right, I think what we're going to do is we're going to jump up to here, and I'm going to find the particular solution for x. So we have the auxiliary equation is m squared minus 8m plus 20 equals 0. On my calculator, let's very quickly solve this equation. That's 1 minus 8 and 20. I get that m is equal to 4 plus or minus 2i, so that my complementary function is x equals e to the 40, that's from the real part, and then a cos 2t plus b sine 2t. There is no need to do a complementary function here. Why did I do that? We don't have a particular integral, so this is actually just the general solution straight away. I don't need to do a particular integral because of the fact that it is equal to 0. By the way, if you couldn't do part A, you can definitely do the rest of the question because they've already told you what this differential equation is. So I don't know if I can actually even go about trying to find out anything with this. I mean, I guess I could use this fact and this fact here. I could do that right now and differentiate it. I might actually just go ahead and do that because I can use that. Okay, so I'm going to do that. I might not usually have done this, but I think I probably will do it. So I'm going to actually find out what dx dt is, which is the same as x dash. So I'm going to differentiate the e to the 4t. That's 4e to the 4t, a cos 2t plus b sine 2t. And I still have the e to the 4t when I differentiate the next part. Cos goes to minus sine, so it'll be a minus 2a sine 2t plus 2b cos 2t. And I know that when t is equal to 0, dx dt is equal to 8. That should tell me something, at least. So, by the way, when I differentiated this, I was just using the product rule, okay? So 8 is equal to 4 times by 1, you would then have the a. And then for this next part, we would have the 2b for this. Is that right? Yeah, we would have the 4a because the sine part goes here. This is a 1. Cos is just going to be 1, so it's a 2b. So I'm not going to be able to do anything more with this because I've got a mixture of a and b. But 8 is 4a plus 2b, or 4 is equal to 2a plus b. Okay, we'll come back to that and see if we can finish solving it. I think what I'm going to have to do now is I'm going to have to find out the general solution for y. So I'm going to find the general solution for y. And do you remember I said something in this box? I said I'll read it later. To find the general solution for y, you do not need to repeat this process up here to find this new equation for y. We actually already have the information ready to do this because we just differentiate to find x dash r. We have already done that over here. We just need to substitute back into my earlier equation for y and go from there. So when we talk about this earlier equation for y, let me highlight this. My earlier equation for y, where did I put that? Ah, here it is. This is my earlier equation for y. If I substitute x and x dash into that equation that is green, it'll tell me what the solution is for y. So y is equal to 3 over 2x minus a quarter x dash minus 1/4 x dash. Now this is the part that's going to be an awful lot of stuff to write down. I'm going to try and keep as much of this visible on the page as possible. This is x that I'm talking about that's going to get substituted in here. So it is going to be 3 over 2 e to the 4t a cos 2t plus b sine 2t, and then I'm going to be doing minus a quarter of x dash, minus a quarter of this expression. So minus a quarter of the first bit is just going to be e to the 4t a cos 2t plus b sine 2t, and then there's going to be minus a quarter e to the 4t, this is never going to fit, minus 2a sine 2t plus 2b cos 2t. Okay, it doesn't look particularly pleasant, but I think we're going to be able to probably handle what is going on with this because we now know that when t is equal to 0, what did we say? X is equal to 6y. X is equal to 6y. So let's see what x is equal to. When t is equal to 0, x is equal to, looking at this, that's 1, that's 0. X is just equal to a. Okay, that's fine. And y, when t is equal to 0, let's look at this expression here and see what y would be equal to. It would be 3 over 2 from this part. That would be 1, and that would be a. So it's a 3 over 2a. Remember, sine we can ignore because it's going to disappear. We would then have a minus a for this part because you have a minus with the a. And then for the last part, being really careful, it is a minus quarter and a 2b. Minus a quarter times 2b is minus a half b. In other words, y is 3 over 2a minus a. That is a half a minus a half b. And we know that x is equal to 6y. So x is equal to 6 lots of y. So a is equal to 3a minus 3b. So that's 2a minus 3b. And earlier on, we had another equation. So I'm going to take this one and solve them simultaneously to find out what a and b are. These questions are no joke. So there is a 2, a minus 3, and a 0 for the bottom one. And then a 2, a 1, and a 4. And we then get from the solution to those two equations is that a is 3 over 2 and b is 1. We're not finished because we actually need to find out the particular solutions for x and for y. So we now know that if a is 3 over 2 and b is 1, hence x is equal to, looking at the equation for x, it's really important to keep your page well organized here. Okay, it's this equation. So I know that a is 1.5 and b is 1. So x is e to the 4t a cos 2t plus 1 sine 2t, and y is equal to quite a lot of stuff that we need to work out here. I'll see if I can do this in one calculation. I'll do all of the cos parts together, okay? So this is a cos part, this is a cos part, and this is a cos part. So bear with me with this. I have a 3 over 2 times by a, so that's a 1.5 times by a, which is 1.5. Then I'm going to be minusing an a, so I'll be minusing a 1.5. And then I'm going to be doing minus a quarter times by 2b, minus a quarter times by 2. So I get a quarter. The cos part, and I'm trying to do this to keep the video kind of a bit more contained, it is the cos 2t. And then for the sine parts, we have here, here, and here. Like on reflection, I think it's probably better to actually substitute them in directly rather than trying to calculate this as quickly as possible. But I am trying to be as efficient as possible for these videos. So I'm going to do the 3 over 2 times by, this for the sine part, the 3 over 2 times by b, which is 1, so that's 1.5 times 1. I'm then going to be subtracting b, which is subtracting 1, and then subtracting a quarter multiplied by minus 2a, so that's minus 2 times by 3 over 2, and that gives me 5 over 4 sine 2t. So I've got the particular solution for the ladybirds and for the beetles here. Incredibly tough questions, so much thinking, and like I said, I think it's probably better to take your time with this and actually writing these things out rather than trying to do it in your head like I just did there. Like I've said, trying to save some time for this video. So for part C, we are going to determine the maximum population of ladybirds. Maximum population of ladybirds. Well, we know that maximum is to do with you differentiate and set it equal to 0. So I think when we're looking for this maximum population of ladybirds, we'll be saying that dx dt will be equal to 0, as being predicted by the model, and we're going to find the approximate number of days after the start of the study that this maximum should occur. Now I've plotted these graphs. These are the two graphs that we have here. I'll kind of discuss those later on. We're going to continue with the question, and we're going to do part C, which is to find the maximum value. In other words, my pen is being a bit strange here, is that dx dt is equal to 0. So let's differentiate x. I know I've differentiated it somewhere earlier on, but I think with the a's and b's and stuff, I might actually even find it easier to do just like this as well. Okay, so I'm going to differentiate it, and I've actually got the function already written up there for x. So let's go straight in and find out what dx dt is. So dx dt is differentiating this function. I will pull the 4 down. It's 4e to the 4t, 3 over 2 cos 2t, plus sine 2t. And then I'll differentiate just the inside part. So that would be my e to the 4t. Cos goes to minus sine, and that extra 2 is going to come out. So it's going to be minus 3 sine 2t. Sine goes to cos, so that will be a 2 cos 2t. Now, because it's going to be equal to 0, I get that 0 is equal to this expression. Like this. Okay, so because e to the 4t cannot be equal to 0, I can just go and just cancel that through immediately like this. So that the equation I get left with is 4 times 3 over 2. That is going to be 6 cos 2t. and then the 4 times the sine 2t. I then have the minus 3 sine 2t, and I also have the 2 cos 2t as well. So I just need to solve this equation. The coses are going to simplify to an 8 cos 2t, and then I just have the plus sine 2t like this. I think the way I'm going to solve this is just by converting it to like a tan equation that we've got here. So I'll divide by cos. If I divide by cos, I get this. So tan 2t is equal to minus 8. So I will do the inverse tan on minus 8, obviously being in radians mode still. This gives me a negative value, which is not really ideal because we're expecting a positive value. But remember, if you want to find another value for tan, you can just add 180 degrees or pi radians to it. So that instead, I have this 1.69515, meaning my value of t is going to be that value halved. So the 1.69515 halved, which is 0.847575 blah blah blah, and this is months. And I'm going to find out what the value of x is here, and just going to find out that value of x by substituting it straight into this formula, and I've got it stored in my calculator. So this will be e to the 4 answer multiplied by 3 over 2 cos 2 answer plus sine 2 answer, close off the brackets, and we get that x is equal to 23.9246. Remember, this is in hundreds, so we need to multiply it by 100 to get the population of the ladybirds. And yes, I'm doing that on my calculator. This is 2,392 ladybirds. Whoa, not ladbirds, but ladybirds. And we'll do that to the nearest ladybird for this. And the time that this will occur, well, I'm going to multiply it by 30. Obviously, you can multiply it by 31. It's really just an approximate time for this. But because to go from a month to days, I will do 0.847 blah, blah, blah. I will multiply that by 30. They would accept, I think, a couple of answers for this. So I'll tell you what I think they would accept in just a second. 0.847575 times by 30. Yeah, that's 25.4. I'm going to say this is 25 days. I actually think they would accept 25 days or even 26 days for this because it's occurring on the 26th day because it's 25.4, but approximately 25 days. Or if you wrote 26 days, I'm sure that that would be accepted as an answer. I mean, I wrote the question, so I'm definitely going to say that this is something that could be accepted. So, last part of this question is to criticize the use of the model in the long term. Well, if you do have a graphics calculator, or if you're doing this with Desmos or something, we can see that something quite strange happens with the graphs. They both go to a negative population. So previously we looked at what happens as t becomes large. Well, as t becomes large, this thing here becomes very, very dominant. You get an exponential function, meaning huge things. But this part here, these two trig terms, we can combine them using an harmonic identity like an r cos theta plus alpha or an r sine theta plus alpha. And no matter what t does, it's going to keep going positive, negative, positive, negative, positive, negative. So this is why with long-term t behavior, it just gets very extreme positive and very extreme negative. So instead of that, we have to just say some of the time it's going to predict a negative population. And again, having a graphics calculator just gives you that advantage of immediately seeing that the model predicts negative populations at some point. So the long-term part is the model predicts negative populations. My pen is being very strange. The model predicts negative populations for some values of t. So not very good. That's a criticism that we could have. And again, the other thing we could say is it predicts like huge kind of population growth and also negative populations. Now, another question that they could have asked is when does the ladybird population die out? By the way, I know this red one is the ladybird one because we said that it occurs at 0.847, that maximum. And you can see this maximum for the ladybirds is roughly at 0.847. And this is corresponding to the 23.9 part that we've got here for that maximum part. This one must be the beetles. They could have asked you, when does the population of the ladybirds die out? In other words, when does it equal 0? Meaning you could just take this equation and set it to equal 0 instead. However, once that becomes 0 and goes negative, this part of the graph is no longer reliable because it's using information from negative populations in this original part that we've got here. And it doesn't really make sense to even do any calculations with a negative population because we know that that wouldn't happen. So incredibly long, demanding questions that we've got here, but really one of my absolutely favourite topics for this. If you have stuck with me through all of these chapter summaries, it must mean that you've got some exams coming up. So I just want to take this opportunity to thank you for watching all of these videos and to wish you the absolute best of luck in all of your upcoming exams. Thanks for watching these videos, guys. Bye bye.